Dr. Bernard Francq. Bernard is, more than anything, is a friend of mine. We had a chance to present at the same conferences of NBIS in Europe, and it's his second visit to Israel. The first one was on June 2015, right? And I'm honored to invite him again to give a talk. ברנרד הוא סטטיסטיקאי ראשי, Principal Statistician בחברת תרופות, אחת הגדולות בעולם, GSK. הוא סיים MSc בביוכימיה, הנדסת ביוכימיה, ו-BSc ו-PhD באוניברסיטת UCL בבלגיה. ברנרד בעצם עוסק בעיקר במחקר, אבל מאוד נהנה להרצות, ובתור מי שצפתה בהרצאות שלו בעבר, גם בארץ וגם בחול, הוא מאוד נהנה להשתמש ב-animation, visualization. ההרצאות שלו מאוד ככה מגוונות וכיפיות, אני מאוד אוהבת את ההרצאות של ברנרד. התחומי מחקר שלו הם בעיקר כוללים industrial and non-clinical statistics, תכנון ניסויים, DOE, method comparison studies, הוא גם כתב איזושהי תוכנה בחבילה, בתוכנה של R, ונושאים נוספים זה tolerance, intervals, agreement, equivalence, error invariance, regression, ומודלים, מה שנקרא mixed models. בנוסף, ברנרד התלבט אם להגיד את זה, אני התעקשתי, הוא מאסטרו ווירטואוז של כלי הקשה. אז ברנרד תכף יציג את ההרצאה שלו הרבה יותר טוב ממני, אבל הנושא הוא Equivalence Approach for Multi-Factor Robustness Evaluation with Application in Industry and Vaccine, בתחום של חיסונים, פיתוח חיסונים. בחברת GSK יש תחום של חיסונים, יש תחום של תרופות, מדיסין, יש תחום של היגיינה, משחות שיניים וכאלה. ברנרד נמצא בתחום של הווקסין, של החיסונים. יש בתת מחלקה שלו 40 סטטיסטיקאים, משהו כזה, שעוסקים בסטטיסטיקה וניתוח נתונים, וברנרד הוא הסטטיסטיקאי הראשי, ואני מתכבדת להזמין אותו.
So, in quality by design, we classify the process parameters into critical or non-critical. And the main question that I'm going to focus during this talk is the robustness. And the question is, how far can we change? Thanks. How far can we change our experimental parameters to stay within our target margin? So this is what I call here the flatness. So the flatness describes the desired relationship between the dependent and the independent variables. So, for example, if we want to evaluate the robustness of a manufacturing process, we have a continuous response variable. Basically, it is y. Then, of course, we have the x variables. In this case, we can consider that we have duration and temperature. They are refactored to a domain of -1 and 1, as we always do in DOE. And for this DOE, we have here a central composite design with 6 replicates at the middle point, so the center point, and 2 points, 2 replicates for the other points. And the middle point, here is the reference point. So in the significant flatness, we want to test if the mean response differ between all the points and the reference point. In the practical flatness, we want to test if the mean responses are equivalent. And so usually to do this, we use a TOST. So basically, we want to test if these different points here, is it the same, is it equivalent to the reference point? And so during this talk, we can focus on the practical flatness. So what is the difference between significance and equivalence? So this is just an animation, so you can take a look here on the screen. So we have a target, so that's the line here, the target. And in the classical statistics, when we deal with significance, we can calculate confidence interval and they will contain the true, the target, in 95% of cases. Okay? But then if we increase the sample size, you can see that the confidence interval narrow. And so it's more likely not to contain the target. Then we can switch to 90% if we want. That's not mandatory. But if we want, we can switch to 90 for the equivalence. And in equivalence, we can add an equivalence margin plus minus delta. So this is the gray area here. And then if the confidence interval is completely within, we can say that it is equivalent. If we have an overlap, it is inconclusive. Otherwise, it is non-equivalent. So here, it is the same with the DOE. We want to test if the means are equivalent or not. And so to do this, we can use the TOST. So it is the two one-sided test. So we have two null hypotheses. And usually, it's very basic. We just calculate the confidence interval. And we check if the classical confidence interval here is within the margin. We can use a 1 minus 2 alpha confidence interval, but it doesn't really matter for this talk. So now if we come back to the DOE, we have different approaches to deal with this. So for example, we can have a constant approach. In the constant approach, we compare the 9 design points to a given value, to a constant. So we want to test if all the points here in the DOE are equal to a given target. Or we can also compare the different points of the DOE to the reference point. So here it means that we compare all the points to prediction. Or we can also compare everything to everything. And for this talk, we can focus on these two approaches. So the constant one or the reference one. So the problem is that we work with two samples settings. So we compare different differences. And if you take a look here, so this is the confidence interval for the contrast obtained by the classical confidence interval, 1 minus 2 alpha. So for example, this confidence interval, here we compare the point minus 1, 1 to the reference point 0, 0. And if you can see here, the margin, the target here is 0, because we want to have a difference equal to 0. The margin is here in red, and we can see that all the confidence intervals are in green, because they are all within the equivalence margin. Okay? But the problem here is that we have a multiplicity issue because we have different confidence intervals. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8 confidence intervals. So if we check the coverage probabilities, actually the confidence intervals are calculated with just a t-test, unadjusted. And we can see that the coverage is 95, because the t-test is exact. But the coverage is 95 for all the comparisons. But the problem is that we have multiple comparisons. So what happens if we take a look to the overall coverage? And if you take a look at the coverage overall, you can see that we have a drop. We drop to lower than 85. Now, if we take the exact adjustment given by CDAC, we can see that the confidence interval will be larger because the coverage here is larger, but overall it still doesn't work, while CDAC is supposed to be exact. So why? Why the coverage of the CDAC is not equal to 95, and why the unadjusted T is not equal to 95? Actually, the reason is because we have a correlation. And see, this is what I call here a spatial correlation issue. So all the points in the DOE are correlated to the center point. So that's we can see here on the heat map. So here it is the heat map of the correlation from -1 to 1. And we can see that the correlation is very high everywhere. Now we can zoom in. So this is basically the same heat map. But we can see that the minimum of the correlation is around -0.1. And of course, it's highly correlated in the middle, because the center point here is the correlation of this point to itself. So correlation is, of course, equal to 1. So how to take into account this correlation? So the easiest way is to deal with the multi-T, so the multivariate T distribution. And this can be done very easily in R if you use this function here. And then for the reference approach, we can calculate the contrast. And then to calculate the contrast, now we can use, if you want to adjust, we can use the multivariate T distribution. So the variance is equal to this formula, and everything will be given by the covariance matrix here. And now if we check the coverage with the multi-T, you can see here that for the overall, the coverage is 95, because the multi-T is exact. So multi-T is your friend. Now if we take a look at the quantile for the multi-T, here we have the graph with the quantile on the y-axis, and on the x-axis we have the number of comparison. So on this plot we can see that we have the 9 points in the DOE, but then we can increase the grid. We can calculate contrast for a grid of 5 by 5, 7 by 7, and so on. And if you take a look on this plot, if you use the unadjusted T, the quantile is always the same, because the unadjusted T doesn't take into account the number of contrasts. Now if you take the CDAC approach, the number of contrasts will increase if you increase the grid size, and then the quantile will always increase. But with the multi-T distribution, you can see that the quantile reach a plateau, because actually we have a saturation in a mathematical point of view. And now if you compare, basically this is the same plot, but between the reference approach or the constant. So reference, it means that we compare all the points to the center point. The constant, it means that we compare all the points to a constant value. And you can see that the quantile are basically nearly the same. But what about the confidence interval? So you can take a look on this plot. So here on this plot, we will calculate all the confidence interval for the contrast for all the design points compared to the center point. And we have the reference approach or the constant approach. The target is 0 because we hope that there is no difference, and the margin is plus minus delta. And you can see that for the reference approach, everything is fine except the last point. It is in yellow because we have an overlap. And now we can adjust. And if you adjust, it's slightly larger. And you can see that this last point, for example, is not equivalent to the middle point. So if we work at +1, -1, it is not equivalent to the center point. So now we can check the flatness in a very funny way. So we have here a response surface model with intercept, the main effect, the interaction and the quadratic effect. And then we can calculate the contrast, because we compare here all the points to the center point. If it is in the green, it means that the confidence interval is within the target and the equivalence margin. If it is yellow, it means that the non-adjusted is still within. And red, it means that it is not equivalent. So the middle point is green, because the middle point is compared to itself. So of course, it is equivalent to itself. And you can see here that if you go to the border, most of them are red. So it means that the border points here are not equivalent to the middle point. And now, of course, you can increase the grid. So here it is 3 by 3, but you can take a look here on the screen. So now we can have here 5 by 5. And of course, then you can still increase, like 7 by 7. And then you can still increase and increase. And I think now you understand where we can go. So we can go like this, like this. We can still increase like this. So you can guess what will be the next picture now. You can increase again, again, and again. And so this is the final plot for the robustness. And so this is what I call the flatness area. And so the questions, I can remind you that the question here is, are the predicted means equivalent to the reference level? Reference level, it is 0, 0. It is the middle point here. So the green area means that the adjusted confidence interval are equivalent. So it means that all the points here are equivalent to the middle point because the adjusted confidence interval lie within ±50. The yellow area means that the non-adjusted confidence interval are still within equivalence margin. And the red means that it is not equivalent. So in the practice, it means that if you work here, if you choose duration and temperature somewhere here, it is not equivalent. So the process will not give you the same. Now we can do the same for the constant approach. For the purpose of this talk, for the constant approach, I use also the reference point, but as a constant, and not like a prediction. So on the right here, it is not a contrast. But you can see that we can still get the same plot. It's still the same, doesn't change that much. The green area is a bit narrower here. Now if we take a look to the variance of the contrast, we can get here this heat map. So we can see that the variance starts from 0, because here it means that we compare the middle point to itself. So the variance is 0, of course. And then if you move away from the reference point, the variance increases, as usual. If you move away, the uncertainty increases. That's very basic in statistics. And now if you take a look to the constant approach, this is the heat map with the same scale. So the conclusion on this slide is the variance of the contrast are higher at the corner point. You can see it is red here. And they are lower around the center. You see it is blue here, but darker blue. Now, another way to deal with this is to do it with simulations. And random numbers can be very useful, especially if you have more than 2 x variables. And so to deal with this, we just use random numbers. So you can take a look here on the screen. On the left, it is the contrast approach. On the right, it is a constant approach. In both cases, we compare to the middle point, except that on the left, it is a contrast. On the right, it is a constant. And now here we can use random numbers. So take a look on the screen. And you can see here I'm going to simulate numbers, and it is color automatically green, yellow, orange, or red. And you can see that if you increase the random numbers, at the end, we can get the same picture. So we can get the same flatness area. This is the proof. So here it is the flatness area. On the left with the random points, and on the right with the grid approach. So now we can take a look, we can move forward, and we can take a look to the p-value. Because the problem with this plot here is that, okay, we have the flatness area, but we don't see very well how it changes around the center point. So now if we take a look to the p-values, this is what we get. So here we have the heat map for the contrast approach with the p-value. The middle point is the reference point, so the p-value is 0. Because we are in a TOST approach, so we want to reject the null. And then if you move away from the middle point, you can see that it becomes light, and then yellow, and then red. So the middle point is the estimated intercept. And here I've added, just for the purpose of this talk, the contour here, where we are exactly equal to the middle point. So everywhere here around the ellipse, we get the same response variable than the middle point. And here it is the same for the constant approach. So you see the area is slightly different, and you can see we have here 3 areas with a darker blue. Okay? Now the problem with this plot is, where is the border between significance and not significant, between equivalence and not equivalence? So it's not easy to see that. See, here on this plot it is very easy. The border is between the orange and the red. So for the p-value, actually it's very easy. You can do the same plot, but just change the scale of the color, and you can get this. Here I use 5% as a threshold, and you can see that the flatness area is this area here. So it means that we are equivalent to the center point if we stay within this area. And here it is the same for the constant approach. Now, just for fun, imagine that now we want the response variable to be equal to 350 plus minus 55, just for fun. So what we get here is the inequivalence area. it means that it is the area where the adjusted 90% confidence interval will lie between 295 and 405. So we can get this plot. The green here means that the confidence interval will be lower than the lower confidence interval. Here in blue, it is a threshold given by the upper confidence interval. And in red, we are exactly equal to 350. And so this is what we want. We want to be equal to 350, but plus minus 55. And you can see here, I did it on purpose, of course, just for fun. You can see that we have two different areas, the white here. And now, just for fun, you can take a look on the screen here. I'm going to pick some points here and take a look on the right what happens with the confidence interval. So we must be equal to the target because we want 350 plus minus delta. So here, take a look on the screen. And you can see here, I'm going to take some points like this. And you can see the confidence interval are on the right. If it is red, because the confidence interval is larger. And now, just for fun, I pick here a point on this small island here. And you can see that here we are not equal to 350. There is a kind of bias. But the confidence interval is still within the equivalence margin, so it is good. So that's why it is white here. Okay? Here, this point, I put it in orange because it is 350, because this point is on the contour. But the confidence interval is borderline. Now, a last question about this. What happens if we have only an intercept model? Because here what we test is the robustness. So what happens if your process is completely robust? So what happens if everything is flat? So what happens if there is no main effect, no interaction, no quadratic effect? What happens if the process is completely robust? So you don't have any model, it's only an intercept. So you can take a look here on the screen. So this is the heat map of the correlation that I show at the beginning of the talk. So I can remind you that this is the heat map of the correlation. The center point is compared to itself. So the correlation is 1 in the middle point. And then the correlation decreases if you move away. But this is the heat map given by the response surface model. So now what happened if you have only an intercept model? So take a look on the screen. Here I'm going to move to an intercept model only. You see, so we can click here for the animation to an intercept only model. And you can see that if you have only an intercept, so if the process is completely robust, all the points are correlated, and it is 1 everywhere. And you can see that the confidence interval for the reference approach collapse, and the confidence interval for the constant approach converge to the classical univariate confidence interval for a mean, because we have just an intercept, so it means that everything is the same basically everywhere. Now, just a few words about the power and the sample size. Imagine that you want to calculate the power for a DOE in a robustness point of view. So for example, imagine you have just basic DOE here with x1 and x2. We have 5 points, so the middle one and the corner. And here they are tested 4 times, so 4 replicates everywhere. And so we can compare the power with the multi-T distribution to the classical TOST approach. So with the classical TOST approach, it means that we compare all the points to the center point. And if we check the power, we can say that with the classical power, with the classical TOST approach, the power is around 60% here. And overall, we have only 24%. Now, if you use the multi-T distribution, the power is very high. And overall, we get 88%. So that's extremely good, because the power, you can see, collapsed to 24% with the basic TOST approach. So why? Why we have such an increase, such an improvement of the power? Because the full sample size is taken into account with the model when we do the contrast, and not in the naive TOST approach. And moreover, we have a strong correlation that is taken into account by the multi-T distribution. And just to conclude with the power, the sample size should be double if you want to reach the same power with the classical TOST approach. So to conclude, multi-T distribution is the best. Thank you.
Truly fascinating. I mean, your talks are good, but they become even better, so I don't know. The contrast looking at is affected by the experimental error of the experiments. Okay, assume you had previous data that you had collected in other, how would you, that would be a third option, right?
Yes.
That would depend on that. And I think in most cases, people come with data. You know, the real story is they have some Excel spreadsheets in their pockets. It's not, you know, we start from. So that would be a third option. And the second thing I was wondering about, eventually in the design space, you have to turn it into standard operating procedures or something that production is supposed to be using. And they're used to one-dimensional limits. So the proper representation of this design space is also a challenge. You know, and I don't know if you have any thoughts on that.
Yes, thank you. Yes, indeed. And it becomes more complicated if you have more and more X variables. Yes. And for the question about data, historical data, for example, yeah, there are different options like the Bayesian statistics, for example. You can play with prior, or yeah, we can include this knowledge into nearly the same mathematics that were presented here.
יש עוד שאלות? לברנרד?
You're using the multivariate T, right?
Yes.
Did you consider using Hoteling's T-square instead?
Yes.
And?
Yes, actually I prefer here the multi-T because it's completely generalizable. And we can take into account here the correlation structure between the different contrasts. But we can use the Autolink or Tukir or whatever. We have also this approach here where we can compare everything to everything, so all the points compared to all points. So this is the third approach here. But basically here, just to sum up, I like the multi-T because it's completely generalizable, and we can take into account the correlation structure.
Okay, thank you.
שאלות נוספות לברנרד? תודה רבה. Thank you.
Thank you.